Welcome to Tech Mastery Guru, and welcome to part 2 of the AI Agent Playbook, From Prompting to Production. This video provides practical and foundational knowledge for building powerful AI agents, cutting through the hype to deliver real-world insights for creating intelligent systems. Today, we'll dive into the RAG pipeline, a crucial technique for AI agents. RAG, or Retrieval-Augmented Generation, allows agents to blend external, proprietary data with their existing knowledge, leading to more accurate and contextually rich responses. It involves chunking, embedding, indexing, querying, synthesis, and optional reranking. This diagram visually represents the conceptual RAG pipeline, illustrating the offline ingestion phase where documents are processed and stored, and the online retrieval phase where user queries are answered using the index data. When choosing a vector database, the main goal is to avoid infrastructure sprawl. Options include pgvector for seamless Postgres integration, Pinecone for quick deployment and scalability, and managed cloud services like Vertex AI Vector Search for those already invested in a specific cloud provider. This pseudocode demonstrates pgvector usage in Python. It shows how to store document embeddings and query for semantically similar content directly within Postgres, highlighting its simplicity and efficiency. Moving to advanced RAG, consider chunking strategies and hybrid queries. Alternatives include Agentic RAG, which gives agents tools to reason, REAG for enriching text chunks, and full context loading for large context windows. Remember to start simple before over-engineering. A conceptual hybrid query combines vector similarity search with metadata filtering for highly precise results. The pseudocode illustrates filtering by year and category alongside semantic search, efficiently narrowing down information retrieval. Multi-agent systems operate like specialized teams, with different AI agents collaborating on complex tasks. Roles include research, writing, code, supervisor, and review agents. The agent supervisor pattern involves a central agent coordinating others as tools. Effective multi-agent systems rely on clear coordination patterns. This includes the agent supervisor model, integrating control flow with human feedback at checkpoints, and defining complex tasks as structured workflows that agents can use as reliable tools. This diagram illustrates the conceptual supervisor pattern, where a user's request is broken down by a supervisor agent, which then delegates subtasks to specialized agents like a research agent and a writing agent, coordinating their efforts to fulfill the request. The agent-to-agent, or A2A, protocol from Google standardizes communication between agents, addressing N-by-M integrations. It enables decentralized communication, capability discovery via agent.json, and flexible interaction over HTTP and JSON RPC 2.0. Microsoft actively supports its adoption. This diagram outlines conceptual A2A discovery. Agent A, as a client, discovers the capabilities and endpoints of Agent B, hosted on a web server, by querying its agent.json file. Agent A then makes a JSON RPC request based on the discovered capabilities. Evaluating AI agents requires evals to measure quality. These provide quantifiable, graded metrics, typically scoring between 0 and 1. They bridge the gap from traditional software testing to AI's probabilistic outputs and are essential for both unit and system testing. This diagram highlights conceptual evaluation points within the RAG pipeline. Evals measure context precision, faithfulness of the answer to the context, and answer relevancy to the query, ensuring quality at critical stages. Textual evals measure accuracy and reliability. This includes detecting hallucinations, ensuring faithfulness to context, assessing completeness of information, and evaluating answer relevancy to the original query. These are critical for trustworthy AI-generated text. Beyond accuracy, we evaluate context and output quality. Context evals check precision and recall of retrieved information. Output evals assess tone consistency, prompt alignment, and summarization quality, ensuring agents deliver appropriate and useful responses. Other evaluation types include classification evals, agent tool usage evals, and prompt engineering evals. Human data review and A/B testing are also crucial for catching nuances and validating user metrics, ensuring a holistic understanding of agent performance. This diagram shows a conceptual human review flow. An AI agent's query, context, and response are stored in production logs. A human reviewer samples bad traces, corrects responses, annotates issues, and adds them to a future evaluations. Local development essentials include an agent front-end, primarily a chat interface using streaming protocols. Crucially, full agent logic should never reside client-side to prevent API key leaks. Helpful back-end tools include a chat interface, workflow visualizer, tool playground, and tracing/evals visibility for efficient debugging. This diagram illustrates a conceptual local development environment. It shows a developer's laptop hosting a chat UI frontend and a tool playground, both interacting with an agent server backend. The backend exports traces to an observability UI for monitoring. Deploying AI agents brings unique challenges. Unlike traditional web apps, agent workloads are complex and often long-running, exceeding serverless function timeouts and bundle size limits. Auto-scaling managed container services are recommended for robust and scalable deployment. This slide, titled Conceptual Deployment Architecture, provides a visual representation of how an AI agent system might be structured for deployment. Multimodal agents are a rapidly evolving frontier. Image generation has reached consumer-grade quality, enabling rapid ad creative and asset prototyping. Real-time voice interaction, however, remains challenging due to low information density, high processing costs, and the complexity of voice activity detection, often requiring a multi-step pipeline. This diagram depicts a conceptual voice pipeline. It shows a multi-step process involving speech-to-text, a large language model for text-to-text response, and text-to-speech, illustrating how real-time voice agents process and generate spoken interactions. For code generation, safety is paramount. Agents utilize feedback loops to iteratively refine code, and secure sandboxing, Docker Firecracker VM, is essential to prevent dangerous commands. Code analysis tools like linters also provide ground truth feedback for robust code development. This slide, titled Conceptual Sandboxed Code Execution, illustrates the process by which generated code is run within an isolated environment to ensure safety and prevent unauthorized access or malicious actions. The agent space is rapidly evolving. We anticipate improvements in reasoning models, autonomous agent learning paradigms, and the growth of synthetic evaluations. Enhanced security imperatives will become crucial, and everyone in this field will remain a perpetual beginner due to the relentless pace of change. Key takeaways include recognizing that agents are more than just LLMs, using structure like workflows and RAG to manage complexity, and embracing observability with tracing and evals. The ecosystem is standardizing, and continuous learning is the most important skill in this rapidly changing field. This slide, titled Conceptual Build, Measure, Learn Loop, visually represents an iterative development process that emphasizes continuous improvement through cycles of building, measuring outcomes, and learning from the results. Thank you for watching. We hope this video provided valuable insights into the exciting world of AI agents. For more deep dives, insights, and updates, be sure to follow and subscribe to Tech Mastery Guru on your favorite platforms.